So welcome to our this is the 7th lecture in our series. Let me put down the title. Now, in the last lecture I was instructed by the operators here to write a little bit bigger. So, I am going to try to stay with a slightly bigger print today and see how that works out. So, let me begin with so the title is Linear Codes and Linear Independence. I will begin with a summary of what we did last time. So, we looked at example rings and their classification. Then we moved on to a different example of an algebraic structure, which was vector spaces. Here we looked at 5 examples. And we looked at derived properties. Excuse me. Then towards the end of the lecture, we started talking about subspaces. And we talked about how one would go about testing for the presence of a subspace. Before we get to that, let me just go back to our previous lecture. We will quickly browse through it. So, here is the part where we are talking about different types of rings and their classification. Where you see the light blue, those are the example rings that we classified. I expanded a little bit on the finite field of 2 elements, because we will be using this structure very often. And there you have the 5 examples, actually a 6th as well. And then after that we went on to talking about vector spaces, where I defined what it was meant, or what is meant by a vector space. And I am going to dwell on this for just a minute, because when we talk about subspaces I will make a reference to these axioms. So, in order for an algebraic structure to be a vector space, you need to satisfy basically 9 axioms, and you can clump 5 of them together by just saying that the collection of vectors together with addition forms an abelian group. Okay. So, that in some sense is the compact way of stating 5 axioms altogether at once, and then that is followed by 4 other axioms having to do with scalar multiplication and the interaction with vectors, right. And those axioms are closure under scalar multiplication, associativity of scalar multiplication, the 2 distributive laws, that is that scalar addition distributes over vector multiplication and so on. And then finally, that if you take the identity element in the ring and multiply it in the field and multiply it with the vector, you get the vector back itself. Okay, so 9 axioms. We looked at examples. These are examples in 3-dimensional space. We looked at some other examples as well. Derived properties, Then we talked about subspaces, and I defined what is meant by a subspace. So, a subspace is a subset that by itself is also a vector space, and we looked at examples of subspaces. Okay. Now, it is possible that towards the end of the last lecture there may have been somewhat abrupt cutoff. So, I am going to pick up from this point onwards, and we will talk about the test for the presence of a subspace. So, here the situation is where you have a vector space and then you have a subset of V, which we will call W, and the question is W under the same operations, is this also a subspace? Now, of course, what you could do is, in order to test for the presence of a subspace, you could go back to all the 9 axioms and verify them individually, but that is time consuming. So, this test that is written down over here, namely the test that says that if x and y, that whenever x and y belong to W and whenever C is a scalar that belongs to the field, if you could ensure that x plus Cy is in W, then that is a sufficient and necessary test. Okay. So, let us just see why that is both necessary and sufficient. Okay. So, at the top I am going to repeat the test here. First, let me just pull up some toolbars that I will be using throughout this lecture. All right. So, the test is that x plus C times y must belong to W. And the reason why this test suffices is because 1, setting C equals 1 ensures closure under addition, under vector addition, then next setting equal to x and C equal to minus y ensures that x plus minus 1 times x belongs to W, which is to say that 0 belongs to W. So, that ensures that the identity element belongs. Okay. So, let me just highlight these in blue. So, you have closure, and here you verified presence of the identity element. Setting x equal to 0, C equal to minus 1 ensures that minus 1 times y belongs to W, which is equivalent to saying that minus of y belongs to W. So, that is verifying the presence of the inverse. And lastly, checking that setting x to be 0 ensures that C times y belongs to W. So, this is verifying closure under scalar multiplication. All right. So, in this way we have ensured that this test, the single test over here, is able to take care of 4 of the tests. Now, there are 5 others that remain, but it is straightforward that to note that simply because you have the following situation where you have a collection of vectors and then you have a subset sitting inside, that is W. So, the axioms, for example, like associativity under addition, okay, then commutativity under addition, then associativity under scalar multiplication, distributive property of scalar multiplication, and the action of the identity element, that these 5 other properties follow just from the fact that W is a subset of V. So, there is no verification needed. Okay. So, I will just make a quick note here. The remaining five axioms follow simply from the fact that W is a subset of V. Okay. So, that proves that this single test is all that you need in order to ensure that you have a subspace. All right. Let us apply that in an example. Let us say that your parent vector space, that is V plus F dot, is F2 to the 7 plus F2 dot, and that the subset that you are intending to test is a code, and the particular code that I want to test here is the even parity or the single parity check code. Okay. So, I would like to show you that this is a subspace. Now, there is a simple way to do it, and that is to say that note that X belongs to C if and only if 1 transpose X is equal to 0, which is the same as saying that sigma x I is equal to 1 is equal to 0. Okay. So, we will actually use this equation here. And so, now if X and Y belong to C, then that implies that 1 transpose X is equal to 0, 1 transpose Y is equal to 0, but together these imply that 1 transpose X plus CY is equal to 1 transpose X plus C times 1 transpose Y, and now you know that individually these two terms are 0. So, this is 0 plus C times 0 excuse me, these are scalars. This is 0 plus c times 0, which is 0. So, you are done. All right. So, that ensures that you have a subspace. Thus, the even parity code is a subspace F2 to the 7. I want to point out something here. Note that for the particular case when f is f2, the only non-zero scalar is equal to 1. Therefore, the test x plus cy in W. So, let me say the test x plus cy in W reduces to x plus y is in W. So, in all the coding theory examples where the field is just the field of two elements, because the C over here that appears here is a scalar, and there are only there's only one non-zero scalar here. So, the test simplifies to this. And now, if you go back in your notes and look, you will notice that when we tested for the presence of a subgroup of F2 to the 7, we had the same test. Okay. So, I will just therefore, there is no distinction between subspaces of F2 to the n and subgroups. So, it follows from this that there is no distinction between subspaces of the set of n tuples over F2 and of subgroups and subgroups and subgroups of So, in other words, whether you are testing to see if a particular code is a subspace of the set of all n tuples, or you are just checking to see if it is a subgroup of the set of all n tuples viewed as an additive subgroup, the test is the same. Okay. And now we will, for a brief moment, we will return to error correcting codes and we will make a definition. A linear code of block length n is any subspace of f2 to the n. Okay. And when we say of f to the n, we really mean of f2 to the n plus f2 dot. Okay. All right. It follows from this that every linear code is also a subgroup. For this reason, linear codes are also called group codes. Okay, so that is just a quick remark. Now, as far as examples go, we have already seen that the single parity check code is a linear code, simply because what we did was we verified that it is a subspace, and a linear code is nothing but a subspace. So, it follows from that the single parity check code is a linear code. Example 2. The repetition code. So, here the code is comprised of just 2 vectors, and in order to check that it is a code, you just have to check addition. Clearly, the sum of any 2 code words is a code word. Therefore, it follows that this is also a linear code. So, the more interesting question, so the 2 codes, the single parity check code and the repetition code, are both linear. The more interesting question is, what about the Hamming code? So, the Hamming code, and I will draw the familiar picture again. Okay, so, the Hamming code, if you will recall, is a collection of binary bits arranged within 3 circles in such a way that within each circle even parity is actually satisfied. Okay. So, now so for example, one of these parity equations would tell you that it must be that M0 plus M1 plus M2 plus P4 is equal to 0. Okay. So, by looking at the parity condition in this circle, you get this equation. So, if you do that, then you will see that you can alternatively rewrite the equations in the following way. So, let me just write down in symbols as placeholders for the coordinates. Right. So, these are the 6 coordinates. And we have in all 3 parity check equations. So, the first one checks for 0, 1, 2 and 4. So, I will say 1, 1, 1, 0, 0. The second one checks for 0, 2, 3 and 5, excuse me, 0, 0, 2, 3 and 5, excuse me. The last one checks for 0, 1, 3 and 6. Okay, so, these in a sense represent the parity checks, and now if I just add a column vector and set this equal to 0, 0, 0, then it will be clear that there is an equivalence between the circle diagram and this matrix equation. So, I have M0, M1, M2, M3, P4, P5 and P6. So, let us call this matrix and label this as H. Now, this thing here is our code word and this is the 0 vector. So, what we are saying is that an alternative way of actually describing the Hamming code is simply to say that it is the set of all vectors which satisfy an equation of the form H times C equal to 0, or in other words, the code is simply the set of all vectors which lie in the null space of H. Okay. Thus, the Hamming code is precisely the set of all code words C satisfying H times C equal to 0. So, now we want to verify that this in fact defines a linear code. So, let us apply our test. Now, x in the code implies that H times x is equal to 0, y in the code implies that h times y is equal to 0. So, it follows that therefore, h times x plus cy is equal to h times x plus c times hy. So, this is 0. Therefore, the Hamming code is linear. Okay. But you will notice, just a quick remark here, that in fact what is actually true is that any code which is defined through a matrix by saying that here is a matrix H and the code is defined to be the set of all vectors such that that matrix times the vector is 0, right. So, now the collection of all such vectors is called the null space of the matrix, and it follows from what we have just discussed is that the null space is always a subspace and therefore defines a linear code. Okay. So, note given a matrix H, the collection all vectors x such that h times x equal to 0 is called the null space of H. Okay. So, the null space is written. Okay. So, this means null space of H is the set of all vectors H such that Hx equals 0. So, it follows from this so null space is a term that you will frequently encounter in linear algebra, but also in coding theory. It follows from this that the null space of any binary matrix is a linear code. All right. Now, we will move on to another notion that is introduced in linear algebra, and that is the notion of linear independence. So, we just have a couple of items more to go relating to linear algebra, and then we will be done with it and we will move on to dealing our focus on error correcting codes. So, one is the notion of linear independence. What does it mean to say a set of vectors is linearly independent? Then after that we are going to talk about the notion of spanning. What does it mean for a set of vectors to span a space? And you may have an intuitive idea of it, but the aim here is to try to make that concrete. And when you put the notions of linear independence and spanning together, then that takes you in the direction of defining something that is called a basis for a vector space. And amongst other uses, the basis also is useful because it allows you to define the size of a vector space, in coding theory it is also useful in terms of allowing you to construct matrices that enable you to encode and decode the code, as we will see later. Okay. So, let us go on to the notion of linear independence. The vectors alpha 1, alpha 2, alpha n dot dot dot. So, let me just make that clear here, a little bit clearer. So, this could continue on up to infinity. Are said to be linearly independent if sigma C I j alpha I j is equal to 1 to r is equal to 0 if and only if is possible if and only if C I j is equal to 0 for all j equals 1 to r. So, the test for linear independence is that you are taking a linear combination of vectors, that is you are scaling and adding, you are taking a bunch of vectors, you are scaling them individually and then you are adding, and if that sum is 0, if and only if all those scaling coefficients are 0, then they are said to be linearly independent. Now, what are some examples of linear independence? Example, in R3, okay, so if you are talking about 3-dimensional space, then what is true is that any collection of 3 vectors in R3 which do not lie on a plane containing the origin are linearly independent. Okay. So, I might for example take, if I took 3 vectors like this, if I took 3 vectors like this, and if I could ensure that there was no plane which contains plane through the origin which contains these 3 vectors, then they are linearly independent. Now, I admit that if you haven't had linear algebra, this may be a little bit quick for you, but the reason for including this is that perhaps it is better to give some background rather than none at all. So, that is the spirit in which I am doing this. Another example of linear independence. Supposing I take a matrix of the form So, let us say we take a matrix of this form. Now, if you have taken linear algebra, then you will realize that this is what is known as a row reduced echelon matrix. Okay. Echelon simply means staircase form, and by actually linking these non-zero entries the way I have actually shown it, you can see that there is a staircase pattern that is actually formed. Now, with respect to this matrix, let us say that you are trying to actually prove that the rows are either linearly independent or not. Okay, so, let us go back to the pad, and supposing you try to take let me label these rows. So, let me call this row vector R1, R2, R3 and R4, and I am going to put a superscript T here on each of them, because by default in our course vectors will be column vectors. So, since these are row vectors, I am going to put a transpose, and if I were to ask the question, are these linearly independent, then if you go back to the definition, then the definition asks you to scale these vectors and add them. But it is just obvious, just looking at the particular structure of this matrix, that the only way in which you can take a linear combination of R1, R2 and R3 is if those coefficients are 0. Now, just a note of caution, I am excluding R4. Any collection of vectors which contains the 0 vector is automatically a dependent set, because you can just scale that and get 0 using a non-zero coefficient. Okay. So, the conclusion here is that the non-zero rows are linearly independent. Now, also one might be interested in the columns. What can one say about the columns? So, let us take a look at this. Now, again going back to linear algebra terms calls the first non-zero entry in each of the non-zero rows as the pivot, and by using similar arguments you can actually show that the columns containing the pivots are linearly independent. So, in this case, in the case of this particular matrix, columns 1, 3 and 5 are linearly independent. The columns containing the pivots are linearly independent. So, let me put down 3 are linearly independent. Okay. All right. So, that's it for this example. So, this is example 2. A third example will look another different structure. So, example 3, and by way of this example I will introduce, I will bring back the collection of polynomials that we encountered earlier. So, the setting for this example is the vector space f of x plus f dot. So, this is the setting, and so examples of vectors might be alpha is x plus a, where a belongs to the field, or alpha 1, alpha 2 is x squared plus bx plus c, where b and c belong to f, and alpha 3 might be x to the 5. And again you can actually satisfy yourself that these are linearly independent, that is, there is no linear combination of them in which the 3 combining coefficients are non-zero can actually give you 0. Okay. Excuse me. Can be verified that these 3 polynomials are linearly independent. Now, as you can see, in our examples we looked at 3 examples which were quite different in nature, right. In the first place we looked at 3-dimensional Euclidean space, and we looked at vectors in 3-dimensional Euclidean space. In the second example we were looking at the rows of a row reduced echelon matrix, whereas this last example was related to polynomials. So, that the 3 examples are quite different in nature. The nice thing about actually working in an abstract framework, in the kind of framework that linear algebra provides, is it allows you to simultaneously address these different examples through a common definition and a common notion of independence. Now, what we will go on to is another notion, that of spanning. Again this comes from linear algebra. So, once again we will begin with the definition. A set alpha 1, alpha 2, alpha n is said to span a vector space V if every vector z in V can be expressed in the form z is equal to sigma C I j alpha I j, j is equal to 1 to r, where the C I j come from the field and where r is some integer. So, the notion of spanning is just that you should be able to derive from a certain basic set, you should be able to derive other vectors. As a simple geometric example, one could perhaps consider a picture in 2 dimensions, in 2-dimensional space. Supposing you took, let us say, a couple of vectors, one vector like this, and let us say another vector like this, then you can see that, so this is your x and y direction, that every vector in the vector space can be derived as a linear combination of these vectors. For example, supposing I wanted to derive, let us say, a vector along the x axis like this, okay, then what I could do is I could scale this to some point here, then I could figure out a parallel line here, and you can see that by scaling, so let us call these vectors alpha 1 and alpha 2, and let us say that this is your target vector z. So, in particular this, so let us say that that alpha 1 was this, let me do something here. Let us move this over here, okay. And so let us say that this vector here is C1 alpha 1, is C1 alpha 1, and this vector here was C2 alpha 2. So, that means by scaling the first vector and scaling the second and adding, you are able to recover z. Okay, so, this is what spanning means. This C2 in this particular case would be negative because you are going in the opposite direction, all right, and the fact that these lines are parallel means that you are scaling the same vector. So, this is the idea of spanning, that you can derive other vectors by starting out from these vectors. Now, so we have defined what it means for a set to span a vector space. And by the way, an expression of this form that you see over here, an expression of this form is called a linear combination of the vectors alpha ij. Okay. So, I will just make a quick note of that, and with that we will end the lecture. So, z is equal to sigma c I j alpha I j, j is equal to 1 to r. This example, this is what we mean by a linear combination of the vectors alpha I j, right. So, to summarize what we did in today's lecture is, we started out from test for a subspace, and I went through the test and I showed you why it works. We applied it to verify that in an example. Then I defined linear codes as subspaces. So, we could directly apply the test for subspaces and verify and check that the 3 example codes we had encountered are actually linear codes. Then we defined the notion of linear independence abstractly. We looked at some examples, and now we are examining the notion of spanning. So, that is where we will pick up from in the next lecture. So, thank you.